Hello everybody, welcome into another lesson. So today we are going to continue solving two variable systems of equations, but today we're going to do the method of elimination. Yesterday we did the method of substitution, which all that we're going to do today, substitution will still work. But if you have a system like 4x plus 3y equals 3 and 3x plus 11y equals 13, substitution's probably not the most ideal because you're going to have a ton of fractions. So there is another method called elimination. Now, what do we mean by elimination? The idea is to get these equations in such a way that you temporarily eliminate one of the variables and solve for the remaining variable. Then when you get the value of that remaining variable, you substitute it into one of the original equations and solve for the other variable. So let's look at this system here. We have 4x and 3x. If I take this system here, I multiply the first equation by 3 and the second equation by 4, both of these will end up having a 12x. Or I could go the y route, and I could try to eliminate y instead. I could multiply the first equation by 11, the second equation by 3, and I would have a 33y in both. Either way, I'm going to subtract the second equation from the first. But it's usually best to work with smaller numbers. For me, I'm going to vote to eliminate x temporarily since they have the smaller coefficients. So let's go ahead and eliminate x temporarily. First, we'll take the top equation. We'll multiply that by 3. So 3 times 4x plus 3y equals 3. And then you'll have 4 times 3x plus 11y is equal to 13. I don't know where I'm getting that from. Okay. So the result of that's going to end up being 12x plus 9y equals 9. And then 12x plus 44y is equal to 52. As you see, x in both of these equations now have the same coefficient. We can subtract the second from the first and temporarily eliminate the x variable. So let's go ahead and subtract that second equation from the first. 12x and 12x gets rid of x. 9 minus 44, well, that's going to be negative 35y. That would equal 9 minus 52. Well, that's going to be negative 43. So now you just solve for y. You'll get y equals positive 43 over 35. So we found the value of y. And then for your second step, you substitute that y variable in to one of these two equations, and then you can solve for x. So let's choose the first equation. So we'll have 4x plus 3 times that y value of 43/35 is equal to 3. So that would give you 4x plus 129 over 35 is equal to 3. Well, 3 in terms of 35 is 105 over 35. So that means 4x is going to equal negative 24/35. Then you divide both sides by 4, x would equal negative 6/35. So now we found both x and y values, and you'll get an ordered pair as your solution, being negative 6/35 and then 43/35. So That means geometrically these two lines intersect at one point at the ordered pair -6/35 and 43/35. Again, the goal is to figure out if these lines intersect, where do they intersect? We got the answer here at this ordered pair. If they don't intersect, that means they're parallel. If you just get a true statement, the left side equals the right, that means they're the same line. And we're going to have examples of all that today. All right. We have 2x plus 5y equals 8. And then we have 5x plus 8y equals 10. So another system here, we have 2x plus 5y equals 8 and 5x plus 8y equals 10. We're only using elimination today, so as for me, I'm going to vote we try to eliminate x again because they have the smaller coefficients. So that means we need to multiply the top row by 5. So 5 times that 2x plus 5y equals 8. And then multiply the second row by 2. So 2 times 5x plus 8y is equal to 10. This is all about to turn into 10x plus 25y is equal to 40. And then 10x plus 16y equals 20. Now you have the same coefficient on x, you can just subtract the second equation from the first. So the x's will be gone. This will give you 9y equals 20, which would mean that y equals 20/9. So we found the y value. Now let's plug this into one of the original equations and we can solve for x. Let's pick the top one again because you have a smaller coefficient on y. So 2x plus 5 times 20/9 is equal to 8. So 2x plus 100/9 equals 8. What's 8 in terms of 9? That's going to be 72/9. So that means that 2x would equal -28/9, which means that x itself would be -14/9. So we found the x-coordinate. That means these two lines intersect at the ordered pair -14/9, 20/9. So the solution to this system is -14/9 and then 20/9. All right, so those were some very basic introductory elimination ones. Let's do some fractions. So let's start with some fraction systems. We have 2/5 x minus 3/2 y is equal to 4. Then we have 1/5 x minus 3/4 y is equal to -2. All right, so we got fractions here. Just like in yesterday's lesson, your first goal should be to eliminate the denominator, so we have something much easier to work with. So for the top equation, you have denominators of 5 and 2. That means your common denominator would be 10. So multiply your top equation by 10. you'll end up getting 4x minus 15y is equal to 40. Now, your second equation, you have denominators of 5 and 4. That means your common denominator is going to be 20. So multiply your second equation by 20. You should end up getting 4x minus 15y is equal to negative 40. Well, it doesn't matter which variable we try to eliminate. They both have the same coefficient. Let's see what this is going to look like. So just go ahead and subtract the second from the first. 4x minus 4x is 0. Negative 15y minus negative 15y is also 0. 40 minus negative 40 is 80. Well, you end up with a false statement. You don't get any variable values at all. You just get that 0 equals 80, which we know is not true. 0 never equals 80. What does that mean if you get a false statement? Well, there's definitely no solution. That's true. You can say there's no solution. What else? This is an inconsistent system. That's another way you'll see it. This is inconsistent. So if it's an inconsistent system with no solution, geometrically, graphically, what does that mean? It means the two lines never touch, and if they don't touch, that means they're parallel. So that means these two lines actually are parallel to each other. So they'll never touch. That's graphically what you would look at. If you were to put these into a graphing calculator, you would confirm what I'm saying is true. These two lines are in fact parallel. All right. So now we have 2/3 x plus 1/6 y is equal to 2/3. And then you have 4x plus y is equal to 4. So in your first equation in the system, you got fractions. Well, for the time being, let's go ahead and deal with the first equation, all right? Let's go ahead and do that. If you look at your first equation, you have denominators of 3 and 6. That means your common denominator should be 6. So multiply your entire first equation by 6. You should get 4x plus y equals 4. And then you can leave your second equation alone. That'll also be 4x plus y equals 4. Well, again, it doesn't matter which variables we try to eliminate. In both equations, they have the same coefficients. So subtract the second equation from the first, you would get 0 equals 0. What does that mean this time if you have a true statement? The left side equals the right. There are infinite solutions is what that means. So you have infinite solutions. So every point on the line is going to hold up. And if there's infinite solutions, geometrically, graphically, that means these are actually the same line. They're the same line. They're not different lines. They're actually the same line. Not lines, then. That wouldn't be plural if they're the same line. So there are infinite solutions, meaning they're the same line. All right. We have 3/4 x plus y is equal to 1/8. And then you have 9/4 x plus 3y is equal to 3/8. So 3/4 x plus y equals 1/8. That should be 9/4 x plus 3y equals 3/8. Well, again, let's get rid of the fractions. In this case, both equations have denominators of 4 and 8, so in both equations your common denominator should be 8. So multiply both equations by 8, you should end up getting 6x plus 8y equals 1, and then you should end up getting 18x plus 24y equals 3. Well, if you look here, if we multiply the first equation by 3, you'll actually end up getting the same coefficients for both. But let's go ahead and do that. Multiply the first equation by 3, you get 18x plus 24y equals 3. You can leave your second equation alone. That'd be 18x plus 24y equals 3. Subtract the second equation from the first. Once again, you're going to get 0 equals 0, which means you have infinite solutions, which means they're actually the same line. So you have infinite solutions to this system of equations, meaning that they're actually the same line. And even by inspection, without solving the system, you notice that one equation is literally 3 times the other, or 1 is a third of the other. So yeah, that would mean they're the same line. All right, now we have 1/4 x plus 1/6 y is equal to 1. Negative 3x minus 2y is equal to 0. All right, so definitely we got fractions to worry about in the first equation. You have denominators of 4 and 6. That means your common denominator, your least common denominator, should be 12. So multiply your entire first equation by 12. You should end up getting 3x plus 2y equals 12. And then leave your second equation alone. You got negative 3x minus 2y is equal to 0. Well, you have a 3x and a negative 3x. You can just add the second equation to the first, and you would eliminate the x variable, and actually you'll end up eliminating the y variable. You would get 0 equals 12, which 0 never equals 12. You have a false statement. That means that there's no solution. There are no solutions to this, which means you have an inconsistent system, which geometrically means these two lines are parallel to each other. They'll never touch. Alright, so those were simple fraction coefficients. Let's get into a few harder ones. Let's get into a few more complex fraction systems. So, what if I had something like this? X plus 3 over 4 plus y minus 1 over 3 is equal to 1, and then I have 2x minus y equals 12. So we have a little bit harder fractions to deal with, but the goal is still going to be the exact same idea. In the top equation, you have denominators of 4 and 3, so that means your least common denominator is going to be 12. So multiply the entire first equation by 12, multiply the first term by 12, the 4 cancels, you'll end up with 3 times x plus 3, plus multiply your second term by 12, you would end up with plus 4 times y minus 1 would equal 12. And then you would still have your 2x minus y equals 12. Now, of course, let's simplify this first equation. You would have 3x plus 9 plus 4y minus 4 is equal to 12. And then you would just have 2x minus y equals 12. Simplify the top equation one more time. You would have 3x plus 4y is equal to 9 minus 4 is 5. You subtract that 5 from 12, you get 7. So 3x plus 4y equals 7. Then you have 2x minus y equals 12. All right. Notice though, yes, you have a negative coefficient in the second equation on the y. You have a positive coefficient on the first equation for the y. But your coefficient's 1 in the second equation. I think it's going to be easiest to try to eliminate the y variable temporarily. So leave your first equation alone, multiply your second equation by 4. If you do that, you'll end up getting 3x plus 4y equals 7, and then you'll end up having 8x minus 4y equals 48. Now all you have to do is simply add the second equation to the first, and you can eliminate the y variable. That would give you 11x equals 55, which would just have to mean that x equals 5. All right, we found the value of x. Now we need to find y, stick it into one of these original equations, and solve for y. I'm going to vote for the bottom one since we don't have any fractions. So that means 2 times 5 minus y equals 12. So that means 10 minus y equals 12. So y would have to equal negative 2. So this system intersects at the point 5, negative 2. So these two lines intersect at the point 5, negative 2. And I got more like this. All right. X plus 2 over 4 plus y minus 1 over 4 is equal to 1. Then we have x minus y equals 4. All right. So you have another system where in the first equation you have a fraction. But the good news is you have a common denominator already of 4. So you can just go ahead and multiply the first equation by 4. You'll end up getting x plus 2 plus y minus 1 is equal to 4. Then you still have x minus y equals 4, which if we simplify the top equation, you would have x plus y, all right, equals 2 minus 1 is 1, 4 minus 1 is 3. So you would have x plus y equals 3, and x minus y equals 4. Well, this is going to be real simple to eliminate the y variable. You have a positive 1 on the coefficient in the first equation, a negative 1 on the coefficient in the second equation, so just add the two equations. The y variables will temporarily cancel out. You'll end up getting 2x is equal to 7, which means that x would have to equal 7/2. All right. So we found the x variable. Now stick that value into one of your other equations, into one of your originals. You can solve for y. Let's pick the bottom one since there's no fractions. So you would have 7/2 minus y would equal 4. So that means 7/2 minus y equals 8/2. Which means that y equals -1/2. So these two lines intersect at the ordered pair 7/2, -1/2. That would be the solution to the system, would be 7/2 and -1/2. All right. X minus 1 over 2 plus y plus 2 over 3 equals 4. And then x minus 2y equals 5. So another system where you have a more complex type of fraction. I shouldn't say a complex fraction, but it's a little bit different type of fractions in the first one. Well, you have denominators of 2 and 3, so the least common denominator is actually going to be 6 in your first equation. So multiply your entire first equation by 6. If you do that on the first term, you'll end up with 3 times x minus 1, plus on your second term, you would end up with 2 times y plus 2 equals 24, and then simply x minus 2y equals 5. So let's simplify the first equation a bit. You would end up with 3x minus 3 plus 2y plus 4 equals 24. And then you would just have x minus 2y equals 5. Simplify your first equation one more time. You'll end up with 3x plus 2y equals, okay, so -3 plus 4 is 1. 24 minus 1 is going to be 23. So 3x plus 2y equals 23. And then you're going to have x minus 2y equals 5. Well, I think it's pretty plain to see we can just add the second equation to the first and eliminate the y variable. So let's go ahead and do that. 2y minus 2y cancels out the y, but you'll end up with 4x equals 28, which would have to mean that x equals 7. So we found the value of x. Now stick that value into one of these two original equations and solve for y. I'll pick the bottom one again. So 7 minus 2y equals 5. That means that 2y equals 2, or y equals 1. So these two lines intersect at the ordered pair 7, 1. So yeah, these two lines will intersect at the ordered pair 7, 1. One more like this, then we'll move on to some decimals. We'll deal with some decimal coefficients. All right, x x minus 1 over 2 plus y minus 2 over 2 is equal to 1. And then simply x minus y equals 2. All right. Well, you have, again, fractions in the first equation, so it's pretty plain to see your least common denominator is going to be 2 in the first equation. So multiply that entire equation by 2. You'll end up with x minus 1 plus y minus 2 equals 2. And then you'll have in your second equation x minus y equals 2. Which, if we simplify the first equation, you'll end up having x plus y equals, okay, so negative 1 minus 2, that's going to be negative 3. Now take that 3 and add to 2, you get 5. So x plus y equals 5. And then x minus y equals 2. Well, if you add these two equations together, you can eliminate the y variable temporarily. So the y's will go away. You'll have 2x equals 7, which means x equals 7 halves. Now just stick this into one of your original equations and you can find the value of y. So I'm going to pick the bottom equation, so 7 halves minus y equals 2, which means 7 halves minus y equals 8 halves, which means y equals negative 1 half. So we found both x and y. So the ordered pair that's the solution to this system is going to be 7 halves negative 1 half. So these two lines intersect at 7 halves negative 1 half. All right, so that was it for the slightly more complicated fraction systems. Now let's move on to some decimals. Let's deal with some systems of equations with decimal coefficients. I'm taking my time in showing this stuff because I want to show you what you're really up against. So let's say I have 2.5x minus 3y equals 1.5. And then I have 2x minus 2.4y is equal to 1.2. Okay. Well, we have decimals in both equations. Just like with fractions, our goal should be to get rid of the decimals. If you look at the first equation, you just have 0.5s for your decimals, so you could simply multiply the first equation by 2 to get rid of them. If you do that, the first equation turns into 5x minus 6y is equal to 3. And then in your second equation, not quite as simple, because you have 2x minus 2.4y equals 1.2. Since you have one decimal place, you'll have to multiply the entire second equation by 10 to get rid of that decimal. So if you do that, you'll end up getting 20x minus 24y equals 12. All right, so I'm going to say let's eliminate the x variable. If you multiply the top equation by 4, you'll have the same coefficient on both x variables for both equations. So this would turn into 20x minus 24y equals 12, and then your second equation will be much the same. 20x minus 24y equals 12. Now just subtract the second equation from the first, the x's are gone, your y's are actually gone, and then on the right side you'll also get 0. You get 0 equals 0, which means you have infinite solutions, which means these are actually the same line. So geometrically, these are actually the exact same line, just written two different ways. That's all that is. All right, I got more decimals. Okay, so we have 6.3x plus 7.2y equals 5.4. And then 5.6x plus 6.4y equals 4.8. So both equations have decimals. They both have one decimal place. We're going to have to multiply both equations by 10 to get rid of the decimal. So why don't we start there? Multiply the top equation by 10, you get 63x plus 72y equals 54. You multiply the second equation by 10, you get 56x plus 64y equals 48. Now, this is going to look really bad, but it's actually not as bad as you think. Because if we really stop and take a look at this here, the first equation, what factor do 63, 72, and 54 have in common? They all have a common 9, which means you can divide every term of the first equation by 9. If you do that, you'll end up with 7x plus 8y equals 6. Now look at your second equation, 56, 64, and 48. What do they all hold in common? They have a common factor of 8. If you divide all three terms of the second equation by 8, you get 7x plus 8y equals 6. Much better to work with, right? Then we can just subtract the second equation from the first. You'll get 0 equals 0, which means there's infinite many solutions, which means these are actually the same line written a different way. So these are both two different equations for the exact same line. There's infinite solutions. Alright, we have 0.2x minus 0.5y is equal to, wow, negative 27.8, and then 0.3x plus 0.4y is going to be equal to 68.7. This one looks a little hairy, but the goal should be the same to start with. Get rid of your decimals if you can, which you definitely can, you always can. So there's only one decimal place in each of these equations, so multiply each equation by 10. If you do that, you'll get 2x minus 5y equals negative 278, and then you'll get 3x plus 4y equals 687. Well, you have a negative coefficient on y in the first equation, a positive in the second, that means we should definitely seek to eliminate the y variable temporarily. In order to do that, we'll have to multiply the first equation by 4. So if we do that, oh, this is going to be fun. Hold on. Let's go ahead and do that here. So let's take, I know 2x times 4 for sure is going to be 8x minus 5y, so that'd be minus 20y. But what the heck is negative 278 times 4? That one I don't know. That's why I got my calculator. That'd be negative 1,112. And then you're going to have to multiply your second equation by 5 to get the same coefficient on y. So this would turn into 15x plus 20y equals, all right, now what the heck is 687 times 5? 3,435. Well, at least you have the same coefficients on the y, with one being positive and one negative. So now all you have to do is add these two equations. The y's will cancel out. You should get 23x equals that piece right there. Equals 2,323. So let's see what x equals. $101. So you get x has a value of 101. Now we just stick this into one of the original equations and we solve for y. I'm going to stick it into the second one. So if I take 0.3 times 101 plus 0.4y, set that equal to 68.7, what am I going to get? Something probably a little hideous, but I get 30.3, so I would get 0.4y plus 30.3 equals 68.7, which means 0.4y. Wow, so that's going to end up equaling 38.4, which now I should be ready to find y if I just divide 38.4 divided by 0.4. I get 96. So y equals 96. So that means these two lines are going to intersect at the ordered pair 101, 96. So sometimes these lines won't intersect readily. They won't be visible unless you really zoom out on a graphing calculator, but they do eventually intersect at the ordered pair 101, 96. That problem was not so nice to us, was it? All right. 0.2x plus 0.6y equals negative 1. And then x minus 0.5y is going to be equal to positive 2. You got decimals in both equations. The first equation for sure, let's look at that. In order to get rid of the decimals, you need to multiply by 10. So if you do that, you'll get 2x plus 6y is going to be equal to negative 10. Now the second equation, you only have one decimal and it's 0.5. If you just multiply the second equation by 2, you can get rid of the decimal. So you'll end up with 2x minus y is equal to 4. That actually isn't so bad. And you have the exact same coefficients on the x, so we can just subtract the second equation from the first. If you do that, the x's are gone temporarily. 6y minus negative y turns into 7y. Then negative 10 minus 4, that's negative 14. So you end up now with 7y equals negative 14, so y would equal negative 2. All right, we found y. Let's solve for x. Let's put that into one of these original equations. So x minus 0.5 times negative 2 equals 2, which would have to simply mean that x plus 1 equals 2, so x would equal 1. So these two lines intersect at the ordered pair 1, negative 2. So yes, these lines will intersect at 1, negative 2. Let's do one more decimal one here. But they're going to pull the rug out from under you a little bit. You have 0.05x minus 0.03y is equal to 0.21. And then you have 0.07x plus 0.02y is going to be equal to 0.16. Well, in both equations you have two decimal places, which means you actually, in order to get rid of the decimals, need to multiply both equations this time by 100. So if you multiply them both by 100, the first equation would turn into 5x minus 3y is equal to 21. The second equation, if you multiply by 100, would end up giving you 7x plus 2y equals 16. Now we have a form we can more readily work with. Well, you have a negative coefficient on the y in the first equation, a positive in the second, so I think we definitely want to go to eliminate the y variable. So if you multiply that top equation by 2, you get 10x minus 6y equals 42. If you multiply the second equation by 3, you end up getting 21x plus 6y equals 48. Now you can just add these two equations. You'll temporarily get rid of the y variable. So you would end up with 31x equals 90, which means x equals 90 31st. So that's not quite as nice. If it were 90 30ths, we would have an even 3, but it's 90 31st and 31 doesn't factor at all. Now, it is permissible to put your x into one of these equations that you multiplied by 100 to solve for the y. It really doesn't matter, because if you put it in with the decimals, it's going to get very confusing very fast. I would just put it into one of the equations you multiplied by 100. So why don't we pick the smaller coefficient one of 5x? So if I take 5 times my 90 31st minus 3y, set that equal to 21. This would turn into 450 31st minus 3y equals 21. Well, what's 21 in times of 31? That'd be 651 over 31. Man, that's going to be different. So 450 minus... Alright, so I'll end up with 3y is equal to negative 201 over 31. Well, I don't think that's going to factor. Nope. So my final result should end up being y equals negative 201 over 93, but I want to see if 201 or 93 factor. I think they do. They both have an even factor of 3. That would end up being negative 67 over 31. So these two lines intersect at the ordered pair 90 over 31, negative 67 over 31. And if you really care to, you can get decimals for these. But you're not going to have a good time with it, I guarantee you. It's probably best just to leave it in improper fraction form. Alright, now we're on to the final 4 exercises. These are going to be systems of rational equations, but they're solved much the same way. But let me show you what I mean by systems of rational equations. It's a little bit different than what we've done so far. Let me get a brand new marker here first. Gotta have a good writing marker, don't we? Kind of important. Empty bag. Why I have that, I don't know. Don't mind me. We're almost done, folks. Thanks for bearing with me. Okay. Final 4 exercises are systems of rational equations. So you have something like 1 divided by x plus 3 divided by y equals 2. And then you have 4 over x minus 1 over y is equal to negative 5. Okay, well, you notice your variables are in the denominator. There is one caveat with these variables. Neither of them can equal 0, because if either of these ends up equaling 0, you have an undefined expression, because division by 0 is undefined. So you can solve this system with the caveat that x does not equal 0 and y does not equal 0. Okay? But much the same way, if you look at this system here, you have a positive coefficient on the 3 over y in the first equation and a negative coefficient on the 1 over y in the second equation. If I just multiplied the first equation, if I multiply the second equation by 3, I can get rid of my y term and just solve for x. So let's leave the first equation alone. You'll have 1 over x plus 3 over y is equal to 2, but now multiply your entire second equation by 3, you would get that you would get 12 over x minus 3 over y equals negative 15. Now you can simply add these two equations. You'll get rid of your y terms. You would end up with 13 over x equals negative 13. Cross multiply, you get negative 13x equals 13. which means that x equals -1. Now just stick that -1 into one of your original equations, you can solve for y. So if I take 1 divided by -1 plus 3 over y equals 2, I would simply get 3 over y minus 1 equals 2, or 3 over y equals 3. Now if I cross multiply, I get 3y equals 3, and then y equals 1. And both my x and y solution work because they don't equal 0. So these two rational functions intersect at the ordered pair -1, +1. So they will intersect at -1, 1. And I got 3 more like this, then we'll be done. All right. So we have 2 divided by x minus 1 divided by y is equal to 0. Then we got 4 over x minus 3 divided by y equals -1. Okay. Well, again, we got to have the caveat that x and y both, neither of them can equal 0, because that would make an undefined expression. So x cannot equal 0, and y also cannot equal 0. If we get that for any of these, we have to throw out the solution. It would be called an extraneous solution. Well, if you look here, you have both positive and both negative for your x and y coefficients, so this isn't going to go quite as nicely as our last equation. But if I multiply the top equation by 2, I can make this top equation also have 4 over x, so we can look to eliminate the x variable temporarily. So if I multiply the top equation by 2, I get 4 over x minus 2 over y, which still equals 0, but then my bottom equation stays the same, 4 over x minus 3 over y equals -1. Now go ahead and subtract your second equation from your first. The x terms cancel, so -2y, this would turn into plus -2 over y plus 3 over y would be 1 over y. This would actually equal +1. Well, you'll get y equals 1, which holds because it doesn't equal 0. Now just take that y equals 1, put it into one of your equations, you can solve for x. So 2 over x minus 1 over 1 equals 0, or 2 over x minus 1 equals 0. So then you would get 2 over x equals 1, which would have to mean that x equals 2, which also holds because x doesn't equal 0. So these two curves intersect at the point 2, 1. So these two curves will intersect at the point 2, 1. 2 more of these, then we're done with the lesson. Alright, we have 1 over x plus 2 over y equals 5. Then we have 3 over x minus 4 over y is equal to -5. Alright. So here's your system of two rational equations. 1 over x plus 2 over y equals positive 5. 3 over x minus 4 over y equals negative 5. Well, you have a positive coefficient for the y term, a negative coefficient for the y term in the second equation. I think it's obvious we should try to eliminate the y. If we multiply the first equation by 2, you'll both equations will have coefficients of 4 on the y term. So if we do in fact multiply that top equation by 2, you'll end up getting 2 over x plus 4 over y equals 10. And then you'll still have 3 over x minus 4 over y equals negative 5. Oh yeah, I should make that caveat again. X and y can't equal 0. In fact, I don't even know why I erased that, because it's going to be the same for the next one too. X and y definitely can't equal 0. Side note, got distracted, sorry. But now we can add these two equations. What are you going to be left with? The y's will cancel. You'll be left with 5 over x equals 5, which means 5x equals 5, or x equals 1, which checks out because it's not equal to 0. Now just go ahead and put this into one of your original equations and solve for y. I'll pick the top one. So 1 over 1 plus 2 over y equals 5. So 2 over y plus 1 equals 5. 2 over y equals 4. 4y equals 2. And then y equals 1/2. So these two rational curves will intersect at the point 1, 1/2. So the point of intersection would be at the ordered pair 1, 1/2. One more problem, then we are done with the lesson. Dang it, I did it again. Oh well. All right. 2 over x minus 1 over y is equal to 5. Six over x plus 1 over y is equal to 11. Well, they were actually pretty kind to us for the last problem. You have the exact same coefficients in the first and second equation, one negative, one positive. We're ready to proceed to adding these. But first, let's make sure we understand that neither x nor y can equal 0. Let's make sure we understand that. But let's go ahead and just add the second equation to the first. Well, you're going to get that 8 over x is going to be equal to 16, which would give you 16x equals 8, or x equals 1/2. Well, this x value checks because it doesn't equal 0. Now just stick this into one of your original equations and solve for y. I'll pick the top one because of the smaller coefficient. So that's going to give you 2 over 1/2 minus 1 over y equals 5, which would turn into 2 over 1 times 2 over 1 minus 1 over y equals 5. So that would give you 4 minus 1 over y equals 5. And then you would get 1 over y equals negative 1. Well, that gives you the negative of y equals 1, or y equals negative 1, which also checks because negative 1 doesn't equal 0. So these two curves are going to intersect at the ordered pair 1/2, negative 1. So the answer is going to be the ordered pair 1/2, -1. Alright, so that's it for this lesson. Next lesson we move on to solving 3-variable systems of equations. And besides adding and getting answers, there's a couple of other tricks when you get into 3 or more systems of equations that you can tell more readily if a system is going to have infinite solutions or no solution. So I hope everyone has a great day. Take care.